Additive manufacturing is very flexible, and that's one of the biggest benefits. It presents the opportunity to manufacture on demand, when you need parts and where you need parts.
We can make geometries you can't make by traditional manufacturing approaches. We can make very complex geometry that you can't make by machining.
When you have to modify, or you have a design change, or you want to scrap and start over completely, it's effectively just the cost of your engineer.
Since we've embedded design limitations in everything we've done for 150 years, we have not yet begun to think about what would happen if we didn't have those constraints.
That is technologically a very, very exciting point that we're getting to.
The growth of additive manufacturing has been impressive. Over the past 24 years, it's grown by 26%, and that's the compound annual growth rate over that period of time.
It's up to the imagination today. Almost anything is possible with 3D printing.
Since its beginnings in 1986 with the invention of stereolithography, new additive systems and technologies are being pursued by scores of companies around the world.
Well, 3D Systems really launched this industry 26 years ago, so we had the advantage of being the very first entrants with what we call stereolithography. And that was the first phase of 3D printing. What we found is that the customers worked very closely with us to push the envelope, to help us create new applications that we hadn't even dreamed of. So we started getting involved in things like hearing aid manufacture, making them personalized and customized so they were actually comfortable to be worn. Then what we saw in sort of a phase 2 of 3D printing is we began to see incremental technologies step in and allow for a movement from pure prototyping into what we call direct manufacturing. In the third phase, we're truly democratizing access and accelerating the adoption, really enabling the consumer, people like you and I, to actually use 3D printing and make our own products day in and day out. I think the last 5 years has been very dramatic for the industry. We are seeing other applications of the technology, so end-use manufacturing is exploding. Having just launched Cube and Cubify.com 2 weeks ago, we believe that the consumer market could ultimately dwarf everything we're doing today because there's billions of consumers and they tend to like things that are personalized and things that they create themselves.
Medical and dental devices are a natural fit with additive technology. Customized hearing aids, invisible teeth aligners, crowns and bridges, direct from optical scanning data to the printer. Most are made of polymers, but some are made of metal.
It's advanced to the point where now we're seeing not only models being produced, but also implants in the form of orthopedic implants such as hips, knees, skulls, and so forth.
In January this year, a senior woman with severe osteomyelitis received a complete lower jaw implant made of titanium, the first ever of its kind. Her facial structure was restored and she was able to speak within hours of the procedure.
And what's really exciting about that implant is that it's a fully moving element of the body, so it articulates with the rest of the face, but it's a 3D printed component. And there's some very exciting work using what are called trabecular structures, so using the structure that mimics human bone, so that the titanium gives in the same way that human bone gives. The other really exciting approach is printing with Bio Absorbable Materials. So there's a range of polymer ceramic materials, like epoxy apatite, which we can 3D print with, put into the body in an implant. The human bone will grow into that material, bind around it, regenerate, and then absorb. Because I think today we have about 200 materials that we can use within additive manufacturing. And that sounds a lot, but we still have a long way to go. There are 40,000 engineering polymers, and we have at the moment around 90. So the opportunities are certainly there for materials companies to formulate specific materials for us to use in the future within our additive machines.
When X1 began with casting applications, we began printing sand molds for metal casting. And we started out with traditional foundry materials, silica sands and furan-based binders. Since then, largely because of desires to use more environmentally friendly materials, we've developed a whole series of other print media, both natural and ceramic, and a series of binders, both inorganic and organic binders that are all environmentally more friendly. With the vast improvements in speeds and unit costs in additive manufacturing, we're beginning to see additively manufactured parts approaching the same sort of direct cost levels that you see with subtractive machining. And the beauty of the additive process is that it tends to be transacted exactly in the location you want it, in the design you want, and in the quantity you want.
Additive manufacturing is a complement to subtractive manufacturing. Subtractive manufacturing still holds a lot of value in accuracy, surface finish, large volume parts, whereas additive manufacturing holds a lot of value in complex geometries or mass customization of different volumes.
We can make parts that have a much better strength to weight ratio. So whereas we would have made, let's say, a 1 pound titanium bracket in aerospace by machining it from solid, we could end up with a ½ pound component made additively that's got exactly the same amount of strength, but it's got half the weight.
Aerospace took a pretty big step forward first, mainly because there was a lot of risk to buy down into additive processing. It's not a natural or a normal traditional way of manufacturing parts.
The F-18 by Boeing has really been a success. It's really an example that many people point to because more than 20,000 parts have been successfully installed on that machine, parts that were built by additive manufacturing.
Additive manufacturing has a growing impact on a wide range of industries: aeronautic, medical, and the automotive industry, even extending to jewelry, sculpture, and the toy industry. In Billerica, Massachusetts, Objet makes printers for a wide range of markets. Their high-end printers can mix different polymers on the fly to create multiple discrete varieties.
Digital materials are exclusive to Objet. It's combining 2 of our base materials, of which we have 14, and allows you to get as many as 14 different mechanical properties in the same part. So in total, there's 107 materials you can get from Objet, a lot of those stemming from our digital material technology. One of the advantages of Objet's technology is we actually leverage the inkjet printer technology that's being developed by the Canons, the Oseis, the Ricos of the world. We leverage that engineering. We can advance our technology much faster than some of our competition because there's billions of dollars being invested in that industry that we can just take off the shelf.
The smallest unit of 2D imagery is a pixel. In 3D printing, it's called a voxel. In this case, just 16 microns per edge. Objet's technology can jet a different material for each voxel, placing a rigid one next to a flexible one, and so on, in whatever configuration the design calls for.
One of the advantages of our printers is the ability to serve multiple purposes or multiple designers. So if I'm an RP model shop and I serve 50 designers, I may get 5 different designs, completely different projects that I can place on the tray. And because of digital materials, I can print 1 part rigid, 1 part very soft, and I can have a combination in the middle, and I can print all 5 designers all at the same time. In the case of Iron Man 2, the costume that Robert Downey Jr. wore, a lot of what he actually wore in that movie, the gloves, things along those lines, were actually prototyped using Objet equipment.
It's hard to believe that there are any limits on where this technology could go.
The cost of complexity is actually equal to the cost of simplicity in additive manufacturing. When you take a 3-dimensional object and you slice it into a bunch of 2-dimensional layers, each layer in and of itself is no more complex to make than the layer next to it.
The real challenge currently in the design community among designers themselves is that they're not yet fully aware of the capabilities and limitations of additive manufacturing.
With additive manufacturing, the first thing we have to do with people is uneducate them. Engineers spend years and years learning about what we call design for manufacturing, DFM.
We're not part of a 3D printing industry. We're part of manufacturing. And that means traditional CNC machining as well as additive processes. The two are not mutually exclusive. They work very, very well together.
We always say that additive manufacturing is an enabling technology. We use it to do something new, to make a new product, to enable a new supply chain, enable a new retail model. You don't use it as disruptive technology. It's not here to replace CNC machining or investment casting.
Additive may take some load off of subtractive, but I still think both are necessary for each to have a holistic way to produce parts in the future.
The technology is all about pushing you beyond where you were before, finding new business opportunity, exploiting new business opportunity.
Simplicity and complexity, complete design freedom, and locality of production. When you put all that together, you have a combination that is really dramatic.
With additive manufacturing, there are very few limits. There are considerations, there are limitations, but far fewer.
I think we're going to see a real microeconomy of innovative, creative engineers saying, hang on a minute, I can bring products to market, but I don't need to have a traditional factory anymore. I can be my own factory.
I want to see where it all goes, but I do know this, it isn't a novelty. It's here to stay, for sure.